Hey everyone. Today, what we're going to go through, you can see on the screen, is a full video lesson on solving systems, specifically using the method of substitution. So, we're going to talk about why we can do what we can do, and then we're going to go through a process of the how we use substitution, and maybe just as importantly, how do we structure our solutions so that we're following good communication habits, so that we're making sure that all the formatting that's necessary to solving a system is included. Solving systems, one of the biggest things you're going to need throughout your life in math. So follow along, full lesson. We're covering the whole thing, okay? Here we go. Okay, so let's jump in. You look at question 1. Problem 1 asks you to determine 6x minus y equals 2 for each of these cases, so in each case. So let's just start examining it as we go and not really look at it as a holistic thing. So really I want you to focus in just on problem A. We have to figure out, determine 6x minus y equals 2 for when y equals 2. If we're looking at case A, we're talking about when y equals 2. So I'm hoping for us that this is just background. That is, you take a look at that and you say, well, if y equals 2, then I know that I can sub in a y value of 2. The value of y is 2, and so all we do then is sub in y equals 2. And so the process of us replacing a variable with a constant should be pretty automatic for us. Look what ends up getting created in green. You now have an equation with one variable in it, x. Now we go through and solve. And maybe you're including 6x equals 4 in your solution, but please feel free that if you put in either of those two gold solutions, that we can go straight to a reduced value of 2/3. Okay, so let's take a look at A. We had to figure out what 6x minus y equals 2 was, determine it. If y equals 2, well then that just meant we replaced y with the value it was. That ended up giving us this green equation, and in our background skills, we have the ability to solve that equation. Okay, now I want us to forget that we tackled problem A, and I want us to jump into B. We have to determine what 6x minus y equals 2 is when y equals 2x. So I'm hoping that even though y now doesn't equal a constant, it equals an expression, y equals 2x, something that can change value, we don't care. That it's pretty automatic for us to just say, well then I'm going to sub in y equals 2x. If that's the value or expression that y is equal to, 2x, then wherever I see a y, I can replace it with 2x. And that gives us that equation in green. Well, now, pretty quickly, you can just rely on, hey, that's an equation with one variable. I know how to solve that. And maybe you end up giving me that gold line. Maybe you end up giving me this gold line, but I would really love it if we had jumped straight to x equals 1/2. Okay, let's stop and just take a look at A and B now. Don't even worry about C, let's just look at A and B. In A, y equaled a constant. I just circled it in red. It never changes its value. Y is always 2. So we replaced y with the value it is. In B, y equals 2x. Now that's an expression that can change value. We don't know the value of what 2x is because we don't know what x is. But it didn't impact, it didn't change the way we could go through and deal with the problem. Well, if y is equal to 2x, then I can replace my y with 2x. And now just deal with the outcome. So let's take a look at C now. Okay, in problem C, we get something just a little bit uglier. Okay, it's not a case where now y just equals something with x's or y just equals a constant. Now, y equals an expression with both. I'm hoping our reaction is, who cares? If I have to figure out what 6x minus y equals 2 is, now when y equals 3x plus 4, we should just say, well, if that's what y is equal to, what I circled in orange, then back in my original expression, wherever I see a y, I can replace it with 3x plus 4. And so I can copy out my original expression, or equation, 6x minus, but now instead of me writing y, I can replace that with what it's equal to, a 3x plus 4, and now that's equal to 2. Now, I don't want anybody to be alarmed. If you spotted my error, that's a great thing. But I just want to address the first issue of I replaced my y with what it says it was equal to, what I circled in orange. Okay, the common mistake that I just made in that problem is common. It's going to be the one you're going to make if you make one. My original expression, if you look way back up to my original problem, said subtract y. And if you notice in green, I didn't subtract y. I subtracted the first part of y, but I did not subtract the second part of y. Because y is now made up of two things, of two terms, I have to make sure that I subtract all parts of it. So if you're asking me, the easiest way to remember to subtract all parts of it is to make sure that you put brackets around it. And some of you even learned a lesson or were kind of given a piece of advice when you were younger to say, hey, every time you substitute in, put brackets around it. Okay, I want everybody to take a look at my solution to A. I replaced my y with 2. So if I followed that advice from earlier, I put brackets around it. I just want you to notice those orange brackets really don't make a difference because I'm subtracting one term, the constant. Now I want you to take a look at B. Replace my y with 2x, so I subtract my 2x. Notice those brackets don't make a difference because again, 2x is just one term. But now I want your eyes to go to C. Can you notice those brackets are needed? So whether I choose to write that as my line or whether I choose to come in on my last green line of saying I have to subtract y, and since y is two terms, I have to subtract all parts of it, either one of those green lines are good. Notice if you then went through and expanded your brackets, you come in on my last green line. Okay, now you're just solving that equation the same way you've always solved equations in one variable. Get your variable term all by itself. Get your constant all by itself. Now we can divide out and get our variable all by itself, and there we go. Okay, the focus of where I want your attention right now is actually on that solution to C. Because what we just did in C is going to be a large part of how we solve systems using substitution. Okay, if we understand everything that we just talked about with regards to some theory of some mechanics, then I think that that's going to set us up well for solving systems. Okay, what I want to do now is I actually want to jump in and start solving some systems. Okay, here we go. So what you see on the screen right now is a system of equations. And all we're talking about when we say system of equations is we're talking about multiple equations. So that's all. So when we talk about a system, we're just talking about having multiple equations. So rather than just one equation being true, we have several equations being true. What you see in the system given here, two equations being true. So I'm assuming at this point we understand what solving a system means, that we are finding the point of intersection, or we are finding the x and the y values, in this case, that make both equations true. So theory-wise, I'm hoping that we understand that point. This is a process about how. So what I want to talk about is some formatting. So you're going to see me go through and put everything in blue that would be considered communication as part of your solution. These are necessary things that we want you to write down to make sure that your reader understands the process you're going through. These are also things that when you can build this into a habit, it starts to drive your thinking. So you'll find, if you choose, and you should, to include the blue in your solutions, they almost become a reflex for you that's going to start to drive how you go through and solve systems. They're actually going to make it easier for you to solve. Okay, let's take a look at A. We've been given the instruction to solve, so we need to find, in this case, the x and y values that make both equations true. So the first thing we want to do is be able to talk about these equations. So I'm going to call maybe the first one equation 1, doesn't have to be 1. And I'm going to call the second equation, equation 2. It doesn't have to be 2, but I don't know why you would start with something different. So by me writing down a number and circling it, I just gave that a universal name. Everybody now who sees those two equations can refer to those as equation 1 and equation 2. So that's what we're going to do. We're going to talk about them as equation 1 and equation 2. Now, for us to go through and solve using substitution, we have to go and get to a point where we can create an equation that we can solve. And what that generally is going to mean is we want an equation that has one variable in it. So you'll notice that both of these equations have two variables in them. So individually, we could not solve for the value that a variable is with any individual equation. But if we can combine these two equations in a way that would create an equation with one variable, then that would give us the means to solve. So what I'm looking to do is somehow take equation 1 and write it all with x's or all with y's. Or I'm going to try to do the same thing with equation 2, write it all with x's or all with y's, because I can solve any equation with one variable. So the way that I can do that is to substitute one of the equations into the other one by replacing the variable with an expression that it's equal to. Now, some of us, because we have some experience going through and dealing with equations of lines and thinking about it from a graphical standpoint or a properties of line standpoint, we can sometimes get the sense that what we have to do is isolate an equation for a y. And I need us to know we don't have to do that. That quite often we'll rearrange equations of lines to get the y all by itself, to be able to look at properties of a line, like the slope of the line or the y-intercept of the line. But for the purposes of solving a system, we don't need to get the y all by itself. So what I want to do is I want to take a different approach, intentionally take a different approach. I'm going to isolate and get the x all by itself, just because I assume everybody has a default to get the y. So I want us to take a look at both equations, equation 1 and equation 2, and imagine rearranging either one of those equations to get the x all by itself. What you'll notice if we think about that process is it's going to be easier to get the x all by itself in equation 1 rather than equation 2, because you will not have to divide out that 3. So for the purposes of strategy, if I were you, 100 times out of 100, I'm going to take equation 1 and I'm going to try to get the x all by itself. So I'm going to take equation 1 and I'm going to start to isolate x, which means I can copy out equation 1, and I could just write equation 1 down like that if I wish, and then spend a line going and getting rid of the y to be able to isolate x. But please don't ever feel like you have to waste that first line. If I were you, since equation 1 is relatively straightforward to isolate, I think I'm just going to get rid of the y. So when I write down equation 1, at the same time I'm doing that, I'm going to isolate my x. Now, take a look at what I've written on the screen. Everybody should understand that that equation is equation 1 because I've labeled it as equation 1. Nobody should be looking at that gold equation and going, gee, where did that come from? Because I use my blue equation label, everybody can see that that's equation 1. And if they reference back to the original equation 1, they can just see that it's a manipulation of it. Okay, now that I have that equation 1 isolated for one of the variables, for x, I'm going to sub that into my other equation. What I just came up with, and what I just underlined there in orange, is what x is equal to. It's equal to negative y minus 1. So, wherever I see an x in equation 2, I can replace it with negative y minus 1 because they are equal. So what I'm going to do is I'm going to sub equation 1 into equation 2. And you can see in my blue writing, I am telling the world that that's what I'm doing. Now, I could waste a line copying out equation 2 exactly as it is written to then replace the x with what it's equal to. But please feel free. You could go through and start copying out equation 2, and right as soon as I'm about to write that x, I'm not going to write that x anymore because I know that x has a value or is equal to negative y minus 1. I replace my x with what it's equal to, and I copy out the rest of equation 2. There is the act of me subbing one equation into the other. And if you've been watching this video since the very beginning, you'll notice that's what we did in problem 1, part C. We took a multi-term expression and we subbed it into another equation, and look at what the outcome was. We now have an equation with just one variable, in this case, y. And we should be pretty solid to be able to go through and solve equations in one variable. So I assume that we're pretty solid in where we go. We could go through and expand our brackets. We could then continue on, put together our variables into one variable term, get our constants together, and now we could go through and isolate our variable. There we go. So we solved part of our problem. That is, we ended up creating an equation with one variable, which allowed us to solve for y in this case, for one variable. Our problem was our original system had two variables. So we ended up finding the y value that makes both of those equations true, a y value of negative 3, but we don't know the x value that makes that true. So to go through then and find the x value, we're actually kind of taking a step back. I think this is probably pretty straightforward. All we need to do now is just sub that y value that we just found back into one of our original equations. So if we look back up to our original system, you see equation 1 and equation 2. Since that y value works for both equations, Then we could sub that back into either one of our originals to find its coordinating, its matching x value. So when you take a look back at that system, I really hope that you're thinking about the ease of your work. And therefore, I would hope that we would sub it back into 1. Now, I'm not saying it should be difficult for us to sub y equals -3 back into equation 2, but it is going to be more work. We're going to have to calculate some stuff. There's some bigger numbers involved. And so by subbing it back into equation 1, we're making our life about as easy as it could be. Replace my y with a -3. And now we have an equation with one variable again, with x. Now we can go ahead and isolate that variable, and because we chose the easier of the two equations, then I should have the easier work to be able to go through and solve that equation. And so we've come up with an x value of 2. We have now solved the system. We know that an x value of 2 and a y value of -3 are what make both of those equations true. Now, I'm going to skip the process of us actually taking 2 for x and -3 for y and subbing it back into both equations to confirm our solution. I think that should be okay on your end. The only thing to do to finish off the problem is we actually state our solution as a point of intersection. Or we list the solutions. And we always make sure that when we list them in alphabetical order. So x comes before y. So when I list out my solutions, 2 comes before -3. And there we go. We solved the system using substitution. Now, take a look at the screen because you can see all of our algebra in yellow and you can see all of our communication in blue. I'm telling you that the more and more you practice writing out that blue, you're going to turn solving systems into a reflex action. So make sure that that blue is included in every one of your solutions. Okay, let's try another one. So what you see on the screen now is a system for problem B. I have 2 equations again, and I've been given the instruction to solve. So let's make this as automatic as we can. Label both of your equations, equation 1 and equation 2. Now I want to make a determination of which one of those equations would be easier to isolate for a variable. I scan across all of my equations. Notice I have a coefficient of 2, a coefficient of 3, a coefficient of 2. Those 3 values that I just circled, if I were to isolate for their variable, I would have to divide out that coefficient, which means I might be getting some fractions. However, I've got this y term in equation 1 that has a coefficient of 1. So I would, in essence, have nothing to divide out, which means I can avoid some fractions. So if I were you and I was scanning those equations, I am looking for a variable that has a coefficient of 1 if I'm going to use substitution. And so I see that in equation 1, so I am going to take equation 1 and I'm going to rearrange it. Now, I like to think about my variable term with a positive coefficient. So I'm actually going to think about my y being on that side of my equal sign. And so that y would just be a positive y on the right. That means I want to get rid of that 2, so I'm going to get it over to the other side, which means to get rid of a plus 2, I minus 2, and there is equation 1 isolated. Okay, now that I have equation 1 isolated for a variable, I'm going to take that one equation and sub it into the other. So I'm subbing 1 into 2, so I can now copy out equation 2, but wherever I see my variable of y, I can replace it. And since I'm subbing in multiple terms, I'm going to sub it in brackets. That way I maintain my multiply operation. Okay, now I have a nice easy equation. It's all in one variable. Now is a moment where I think we should be picking this stuff up on our own. So what I want you to do is I want you to pause the video and solve that gold equation that has just x's in it. Okay, give it a shot. Pause it now. Okay, we're back. So I can expand my brackets. Now I want to isolate. So I put my variables together, put my constants together. I'm running out of room. And so I'm going to draw my arrow, and now I can isolate by dividing out 7. Okay, we're good. We've now solved for one of the variables, but we need the other one. So I now need to take that x value, the one I just solved for, and I have to sub it back into one of my originals. Well, if I take a look at equation 2, it's got bigger numbers. Equation 1 has smaller numbers. I'm going to sub x equals 4 into equation 1. So that's going to give me a 2 times 4. And in a lot of cases, you're going to skip that step. You're going to come right in on 8 minus y equals 2. And now we can solve. And however you want to solve for that, I'm hoping that we get down to a y value of 6. Okay, we're almost done. We've actually done all the work. We've solved our system, but we haven't stated our solution. So state your solution as a point of intersection. The x value comes before the y value. And there we go. You'll notice this is the same approach that we took in our solution to A. And you'll also notice that all that blue is driving my thinking. Don't skip the blue. Okay, keep it within each solution. Okay, let's keep working our way through. Let's try another one. Okay, I think we're at the point now where we should be trying to solve this system on our own. So what I want you to do is I want you to go through and try to produce a perfect solution for the system you see in C. That is, you're going to have all of the gold and the blue if you're keeping up with my colors, but we want a perfect solution to C. So let's give it a shot on our own. I want you to pause the video now. Okay, we're back. Let's get a little confirmation. So I can label those as equation 1 and equation 2. I'm going to scan my equations. Do I have a coefficient of 1? And I do in equation 2. I'm going to isolate and get my y all by itself. So I'm going to take equation 2, and I am now going to rearrange it. I've got the same issue, so I'm going to think about that y coming over to the other side. That means that the y will be all by itself if I get rid of that 11, which means I have to subtract 11. Now that my y is all by itself, I can sub that equation, which was equation 2, into the other equation, which is equation 1. Okay, if you made a mistake isolating for your variable in equation 2, then I want you to pause the video now that it's corrected and finish it off. If we get to a point where you see a solution, then what I want you to do, make the correction in your solution and then pause the video and try it on your own. Okay, we always want to be trying these on our own. So now what we're going to do is we're going to take equation 1. That's what it says. It says sub 2 into 1. So I'm going to take equation 1 and I'm going to start copying it out. And now that I get my y, I can replace my y with what it's equal to. And there is the rest of equation 1. Okay, there is my equation with one variable. And now we're hoping that this is pretty automatic. We can expand in our 6. Now I can isolate my variable. To get rid of a minus 66, I have to add 66. So I'm going to take 66 and then minus 15 from it. So that is going to end up being 51. And now I need to divide out that 17. And man, do I really hope that that goes evenly. And it does. There's my 3. Okay, I'm wrapping my solution around. I've now solved for x, so I can sub that x value back into one of my originals, and equation 2 definitely has smaller numbers. Now, it doesn't matter which equation you sub it back into because it is the same for both. So I am hoping that you subbed it back into 2. But just in case we have a little bit where we think in our mind, even the smallest amount, that it matters, I'm going to sub it back into 1. I don't want you to. I hope you subbed it into 2. But we'll just get a little confirmation as we work our way through. If I replace my x with 3, then 5 times 3 is 15. To get rid of that plus 15, I need to minus 15. And to get rid of my times by 6, I need to divide by 6. And so I'm hoping that we get a little confirmation that when you subbed your x equals 3 back into equation 2, you got a y value of negative 5. And you can see that we got the same thing regardless of which equation we subbed into. Okay, I'm hoping that that one gives you a good check. And I'm hoping that we're feeling a lot more confident with solving by substitution. Okay, let's take a peek at another one. So let's take a look at the system that I gave you on the screen. And I'm hoping it's not throwing you a curveball for the fact that we got rid of our x and our y, and now we seem to have equations with a's and b's. Hopefully that's not an issue. What I'd like you to do, go through, solve that system on your own. We'll see if we match up in the end. Okay, give it a shot. Pause the video now. Okay, we're back. So if you are not labeling both of those equations as equations 1 and 2 because you think, oh, look, I know what I'm doing, so I don't need to write that, I think you're making a big mistake. That costs you no time, and it's really going to keep your solution organized. So there's my equation 1 and 2. I'm hoping that we see that the a in equation 1 has a coefficient of 1. So I'm going to want to take that equation and isolate for a. Now, I just have a habit of always writing the other variable term next and the constant on at the end. But obviously, had you written it as 2 minus 3b, to save having to deal with a leading term that's negative, totally fine. I happen to get into a habit the other way, but that's just me. So let's say we took equation 1. We can now sub equation 1 into equation 2. And now as I scan my way across, I've solved for a in equation 1. So as soon as I see my a in equation 2, I can replace it with what it's equal to. I have the rest of equation 2. And now I solved my problem in essence. I have one equation with just one variable. So we can expand our brackets. We can isolate our variable. So let's collect our variable term into 1. Let's get rid of our constants. So right now on the left side of that equal sign, I have 4 subtract 3, which is a 1. If I get rid of a plus 1, then I get a minus 1. And I got that to work out to a nice, neat value of b equals 1. So I'm going to now sub b equals 1 back into one of my originals, and I'm going to sub it back into 1 because 1 just looks smaller. It's got a coefficient of 1 on my a. So I can now replace my b with a 1. 3 times 1 is 3. And I can solve for a. Okay, at the very end, what we have to confirm, when we state our solution, our solutions are always in alphabetical order. So make sure that you put your A solution first and your B solution second. Okay, hopefully that matches up. We're doing great. We'll try another one. Here we go. Okay, so you can see the system we have sitting in front of us. I think this is our last straightforward check. So I want you to work your way through E and hopefully we match up in the end. Okay, pause the video now. Okay, we're back. So we've labeled equation 1 and equation 2. I'm hoping that you can see in equation 2 that our n has a coefficient of 1. So we're going to try to get that n all by itself, which means I have to get rid of a plus 3m. Now that my n is all by itself, I'm going to take equation 2 and sub it back into the other one, to equation 1. Okay, I can start copying out equation 1, and wherever I see my n, I can replace it with what it's equal to. There's my equation in one variable. I can expand my brackets. This case being really conscious of my signs. I can clean up my variables into one term. I can then get rid of my constant and collect that. And now we notice, ooh, I'm going to get something ugly. I'm going to get an m value of negative 19/13. Now, the reason I wanted to walk through something like E, I really want to make sure that I don't put this idea in your head that when we solve a system, we always get nice, neat numbers, like integers. And I'm going to bet that after doing 4 problems together, I had maybe built up that instinct for a bunch of you that you thought when you got an m value of negative 19/13, you made a mistake, that you had goofed up somehow. And I'm hoping we recognize we didn't goof up. It's just that sometimes points of intersection, the variable values that make both equations true, aren't nice and neat. Okay, that doesn't change anything that we deal with. You've just solved for m, for one of the values. Now we need to take that m value of negative 19/13, and we're going to sub it back into one of my originals, and I take a look, and equation 2 is probably going to be easier. So wherever I see my variable m in equation 2, I can replace it with what it's equal to. Okay, all this means is I've got a little bit more work to do when I go through to solve that equation. I need to multiply negative 19/13 by 3. I got to triple it, which means I triple my top. I triple the number of things. So 3 times 19 is 3 times 10 is 30, and 3 times 9 is 27. There's a negative 57/13. And I'm going to go ahead and I'm going to get my n all by itself by getting rid of that minus 57/13. Now, some people are going to want to write this line in, and I'm okay with that. But I hope that we can see we're going to take 8 and we need to add to it some 13ths. We're going to need a common denominator. And so I'm hoping that many of you would say, well, if I know I'm going to need a common denominator, I'm just going to get that right side to be in 13ths, which means I'm going to have to multiply my 8 by 13 to change that fraction. Well, 8 times 10 is 80, and 8 times 3 is 24, so that is a negative 104 plus 57. Now, very quickly, you can see that my 104 over 13 is 8, and then my 57 over 13 is my 57/13, that I've got my correct value. Now all I need to do is simplify the top, and I'm running out of room a little bit, so I'm going to shrink that down. I'm taking negative 104 and adding 57. So that's going to be a 47 that's negative on my 13ths. I can do a quick little check. I would add 47 to 57 to get to 104. So I check out and I'm good. Okay, what's the only problem? I haven't stated my solution. So therefore, and I know I have to list it in alphabetical order, so the m value has to come before the n value. And there we go. Okay, I'm hoping that you knocked E out of the park, but I'm going to bet that I had a number of people stop when you solve for m because you thought you made a mistake because you got something ugly. And I'm hoping that with this one problem, I've now taken away that feeling. No, it is totally fine to get something ugly. In fact, ugly solutions are going to pop up probably more often than neat solutions. So trust yourself in the process. Rearrange your equation. You're always on the hunt if you have a variable with a coefficient of 1. Rearrange, sub it into the other one, solve, sub it back into the original, find your solution. Okay, great job if you got down to that solution, and way to trust your instincts. Okay, I want to try another system that's got something a little different in it. Here we go. Okay, so I want you to take a look at the system that I gave you in F. And you're going to notice there's something different about this system than all of the rest. If you went through to try to solve that system, everybody should be calling equation 1 and equation 2. But now we're scanning every part of that system, looking at all the coefficients, and we're searching for a coefficient of 1. And now we notice we don't have a coefficient of 1. That means that at some point when we go to isolate for one of those variables, we're going to have to divide out a coefficient, which means we may have fractions. Now, what I want to do really quickly is I want to take both of those equations and I want to go through and isolate for each variable. I'm going to do it fast. So I would assume that we are okay to isolate each variable. So if I took equation 1 and I wanted to get the x all by itself, now I'm going to have to divide everything by 3. Notice you get something pretty ugly. If I wanted to take equation 1 and get the y all by itself, notice you get something pretty ugly. If I took equation 2 and I got the x all by itself, hey, I don't get something quite as ugly. If I took equation 2 and wanted to get the y all by itself, I get something just as ugly. So I want you to take a look at all 4 versions of me isolating for either individual variable in either equation. And you'll notice one of them is maybe a little bit easier to work with. Take a look at what happens if I went and isolated in equation 2 for x. You'll notice I don't have 2 fractions, and that might be easier to work with. Now, I want to take a look back up at our original system and maybe see how we could identify that at the very beginning. Take a look at equation 2 and notice I'm going to have to divide 2 out of the 6, or I'm going to have to divide 6 out of the 2. And I notice that 2 does divide into 6 evenly. And so maybe that's what drives my decision. That I may look at all 3 terms within my system and just see, hey, if I go to divide out my coefficient, does it divide evenly anywhere? And if it does, that might make my life easier. So I'm going to erase all of that stuff that I just put down, because all of that was just to help me maybe make my life easier afterwards. With some practice, we may be able to scan, well, 3, 5, and 4. If I divide by any of those values, the 3 or the 5, it doesn't go evenly into anything in equation 1. But if I divide a 2, a 6 into a 5, I notice that at least my 6 does divide by 2 evenly. And so I would be motivated to take equation 2 and try to get the x all by itself. That allows me to say, okay, 2x equals negative 6y plus 5. And so now when I divide out, I actually get at least one integer. So something to help you out when you go through to solve systems where you don't have coefficients of 1. It doesn't mean that because I don't have a coefficient of 1, oh, shoot, well, I can't use substitution to solve. No. The method of substitution is universal. It just might mean that we might end up getting some ugly values or expressions when we try to use it. Okay, I think this is your test now. If you could go through and finish off solving that system, then I think you're pretty solid with your algebra with substitution. So I want you to pause the video and try to give it a shot. Okay, pause the video now. Okay, we're back. So everybody should be taking equation 2 and subbing it back into equation 1. Now, because it's fractions, or there's a lot of fractions, I'm anticipating that this is going to get uglier in our process. But I'm taking equation 1, and wherever I see my x, I'm subbing in what it's equal to. That gave me an equation with y's. I can expand my brackets. 3 times 5 halves is a 15 halves. Now I can collect my variables. I can put together my constants. Well, right now, I'm going to have 15 halves plus 4. So that is a 15 halves plus 8 halves, which is a 23 halves. You may like to write that line in, or maybe you want to get rid of the 23 halves. In either case, we're going to come up with this equation. And now, to divide out a 14 means I'm going to multiply that denominator by 14, and I get a y value of 23/28. Ooh, ugly. So now we've got to finish it off, and I'm just going to shrink that down a little bit because I need to sub y equals 23/28 back into one of my originals. Now, I take a look at my originals, and I'm like, ugh, I don't know which one of those would help. However, you might notice something. I want to show you what's going to happen if I sub this into equation 2. I go through and I start copying out equation 2, and wherever I see my y, I know I need to replace it with 23/28. Now, we may be tempted to multiply that 6 times 23/28 by multiplying the 6 times the 23. But you may notice that my 6 and my 28 both have a common factor of 2. And so if I do a little cross-reducing, 6 divided by 2 is 3, 28 divided by 2 is 14. I can actually deal with some smaller values since I subbed it into 2. So if you look back at my original system, when I had 23/28 and I was trying to decide, do I sub it into equation 1, I can see I'm going to have to multiply by 5. Well, there's no common factors between 5 and 28. So that one told me, don't do that. But if I take a look at equation 2, 6 and 28 do have common factors. So that one became the one that I wanted to choose. Now when I go through to simplify that equation, I'm going to get smaller values. I'm going to multiply 3 times 23. That's a 69/14. And so I'm going to end up dealing with smaller numbers. Okay, I'm going to slide this over a little bit, make a little more room. Now I can go through. Now, I'm going to solve this equation maybe a little different. Previously, I've solved all of them by just getting rid of your constant and getting a common denominator. Now, we should all be comfortable to do with that. That's just fractions. It's just common denominators. But some of us may prefer to eliminate our fractions. And so if we look down at the bottom, our last equation line, we may choose to get rid of our divide by 14 by multiplying everything by 14. And so maybe that's going to make your life a little bit easier because now you don't have to get a common denominator, let's say. 5 times 14 is 5 times 10 is 50, and 5 times 4 is 20. And so when we go through to solve that equation, that may make our life a little easier. Okay, only thing left to do, state our solution. My x comes before my y, and there we go. So I'm hoping that when we work our way through that, we can notice, hey, our original system didn't have a coefficient of 1 on any of my variables. That didn't really matter. We just still pick one of the equations, we rearrange it, get one of the variables all by itself and sub it in. Worst case is we might end up getting some uglier values, but we're okay to work with fractions. Okay, great job. Now I want to change gears a little bit. Okay, so you see on the top of the screen, I've kind of called these special cases. I don't know if they're really special cases, but they might be some situations that don't kind of fall into your normal kind of procedure for us to solve a system. That is, some quirky things might pop up. So I'm assuming we are good with solving systems by substitution right now. So as you're coming into these problems, I'm going to make the assumption that the process for us, the algorithm for us to follow, is pretty nailed down. So I'm going to go pretty quickly through some of that. I just want to address what happens when certain things occur and how we can interpret that. So, as I said, I assume we're really good to be able to solve a system. You see we've got equation 1 and equation 2. I'm going to take equation 1 and I'm going to rearrange it because I see I've got a coefficient of 1 on my x. That's going to get me a 4y plus 8. I can now sub equation 1 into equation 2. I can replace my x with what it's equal to. Oops. I now need to subtract my 8y as I'm copying out the rest of equation 2. Now I can go ahead, expand my brackets. And if I put my variables together on one side, I notice I get 0 y's. Put my constants together on the other side, and I get negative 8. And automatically, I think for a lot of us, we're going to go, okay, this feels a little weird. Maybe you can see where it falls into a special case sort of situation. Okay, how do I interpret what I have now? Well, if I take a look at that equation and I try to solve that equation right now, that equation says 0 times some number, I don't know what that is, has to equal negative 8. And I hope that we're good, that there is no number that when I multiply it by 0, it equals negative 8, because 0 times anything is 0. I can't solve that equation. So I'm hoping we get to it by that point. Perhaps we ended up taking that last equation and we wrote 0 equals negative 8. And I hope that we're good that that equation is not possible. 0 never equals -8. So I'm actually writing down something that's not true. So there's no solution to that equation. Or maybe we're taking the gold and we really have the blinders on. Like, I mean, we're hardly even thinking. We're just going through a process. And we say, okay, to get rid of a times by 0, I'm going to divide by 0. And now we get that that is undefined because you cannot take 8 or -8 and divide it by 0. So we can't define that value. It is undefined. And therefore, there's no solution to that. I'm going to get rid of all of those other colors and leave just the gold. But we get to a point where that gold equation actually has no solution. And therefore, for us to solve the system, there is no solution. That means we can't solve the system. Okay, so what does that mean for the overall system? Well, that means that there is no x value and y value that make both equations true. Okay, what do we have in this situation? Well, I'm going to put down a quick sketch. If I was to take equation 1 and get the y all by itself to enable me to sketch, then I'm just going to jot down equation 1 up at the top. Equation 1 would be 4y equals x minus 8, so y equals 1/4 x minus 2. I'm hoping that we're okay, that that equation would have a y-intercept of -2 and a slope of 1/4, pretty flat. That would be my equation 1. Well, if I was to do the same thing with equation 2, and now I'm going to take equation 2 and get the y all by itself, then 8y is going to equal 2x minus 8. Y equals 1/4 x minus 1. You might be able to see that those two lines are parallel. And if solving a system means that we're finding the points of intersection, then two parallel lines do not cross. They don't intersect. So there is no point of intersection. That we might be able to see why our system actually has no solution. So I want to get rid of the picture so that we don't get lost in any sort of possibility of, oh, so wait a second. So when I solve my system, I have to sketch or I have to graph. No. But we need to make sure that we are good for what happens if we get a no solution part to solving our system by substitution. If we get to a case where we get no solution on that, we have to make sure that we interpret that really what that means, it never has to be written. You can just write exactly what you see in gold. That there is no point of intersection. Okay? A little bit of a special case. Okay, let's try one last special case. You'll see on the screen the system I gave you in H. And I want to address the exact same thing. We are good with solving a system, but what situations may arise? Well, you take a look at both equations and you're like, ugh, none of them have a coefficient of 1. Well, if I took equation 1, though, and I got the y all by itself, then, well, when I divide out my 2, that doesn't help me. I still have a fraction. But when I divide out a 2, at least there I get a whole number, an integer. So for me then to sub 1 into 2 isn't too bad. So replace my y with what it's equal to in equation 2. I can now expand my brackets. Well, hey, this works out really nice. 6 times 3 halves is 9. So since it's a negative 9. Nice. And now when I go to collect my variables and collect my constants, I get that. 0x equals 0. Okay, so how do I interpret that? Well, what that says is 0 times some number equals 0. And we have to try to figure out what number that is. And I'm hoping that we're good. When we look at that gold or the orange, we go, x could be anything. Because 0 times any number is 0. So there isn't one value that x could be. There's actually infinitely many of them. So what does that mean for a solution for us? Well, it means that there are infinitely many solutions for that equation. So I'm just going to get rid of that orange, and I can now state that there are infinitely many solutions. Last time we saw, hey, there was no solutions. This time, infinitely many. Okay, what does that mean? Well, I'm going to let you play around with that one. And whether you want to do some sketches on your own, whether you want to hop onto Desmos and use some graphing software to graph both of those lines. But I think you're going to come up with something that is going to completely justify or make sense for why we have infinitely many solutions on equation 1 and equation 2. Okay, I'm hoping that you picked up for solving some systems using substitution. Pay attention to what is the algebra within the solution and then all that blue stuff I was writing down every time. I'm telling you, if you make sure you write down that blue every time, you're going to drill in that process. Okay, your job now, jump in and get some practice and make it automatic. Okay, best of luck.